10.5, the ratio and roots tests. In the last chapter of our course, we will explore the ratio test, which is a test for absolute convergence. It is quite useful on series that converge quickly and on some of the more difficult series. For example, series that involve factorials or exponentials are often best suited to this test. So here's the ratio test. Let the summation of a sub n be a series of non-zero terms. Number 1, summation a sub n converges absolutely if the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n is less than 1. Summation a sub n diverges if the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n is greater than 1 or equals infinity. And if that limit equals 1, right? Just equals 1, the ratio test is inconclusive. We have to, try and use another test. Okay, so let's determine whether the following series converge or diverge. So here's how you use the ratio test. You're going to take the limit as n goes to infinity. We're going to calculate our a sub n plus 1. So basically, wherever we see an n, we're going to put an n plus 1. Since we are dividing by a sub n, we are going to multiply by the reciprocal of a sub n. So I multiply by that reciprocal, and then I'm putting absolute value signs. Now I just need to work on simplifying this and seeing what I get when I solve this limit. So the limit as n goes to infinity, absolute value. Now think of this as 2 to the n times 2 to the 1. Divided by, now think of this as n plus 1 times n factorial. Because if you were doing factorial, you'd put the n plus 1 first, and then you'd subtract 1 and do that next, and you'd keep going. And so we stop at n factorial because it's going to cancel. So now we can cancel the n factorials and the 2 to the n's, giving us limit as n goes to infinity, absolute value of 2 over n plus 1. And you can see that when I put infinity in, I'm going to get 0. Since 0 is less than 1, the summation, I guess a sub n, converges absolutely. And when I put summation a sub n, it's just trying to save time. I probably, if I was on the AP exam, I probably would have, stated that this was what my a sub n was, so that when I used this terminology right here, they would know what I was talking about, okay? All right. So we have converges absolutely. Now we're going to do the next one. And again, if I see a factorial or if I see an exponential, I always try to use the ratio test. Okay, so a lot of times it does end up working for you. So this one's going to be limit as n goes to infinity. We already have n plus 1 here. So when I replace my n plus 1 with another n plus 1, that's going to end up giving me n plus 2 factorial. This is 3 to the n plus 1. And then I multiply by the reciprocal. And so now to try and simplify, I know this is going to be n plus 2 factorial. So n plus 2, and then I subtract 1. Then that would be n plus 1, and then I can do factorial. Divided by 3 to the n times 3 to the 1, and then times 3 to the n over n plus 1 factorial. And I do that because I know that I want to cancel. So I'm actually getting it set up for canceling. Just make sure that you have the correct Now this one equals infinity. So if our infinity is greater than 1, or you could say that you're using that piece of the test, that means that the summation a sub n diverges. And again, I would have, stated that let a sub n equal this, so that when I used that, it would have been okay with the AP exam. Either that or just rewrite your whole summation, okay, on the AP. You don't have to do that, if you're just practicing. And that's what I was trying to do here. All right, show that the ratio test is inconclusive for the following. Well, to be inconclusive with the ratio test, it must equal 1. So I'm wondering if this will equal 1 when I use my ratio test. So the limit as n goes to infinity, absolute value. I'm putting n plus 1 in wherever I see an n. And then I'm multiplying by the reciprocal. And now I want to simplify to see what I get. So absolute value, trying to think how I would, I probably would take this right here and think of this as n plus 1 to the, n plus 1 to the 1, but I would make my 1 3/3, and the bottom is n plus 1 to the 1/3, and I'm going to bring my n plus 1 to the 1/3 up. And I think I'm going to do the same thing on this side. I've got n to the 1/3, and I've got n to the 3/3 here. So I'm going to simplify by making this n plus 1 to the 2/3, because when I bring this up, it becomes negative 1/3, and then I'm able to add those. 3/3 minus 1/3 is 2/3. And when I probably would bring my n to the 1/3 down. In the denominator, this would be n to the 2/3. And then, since they're both to the 2/3, why not make it n plus 1 over n to the 2/3? And remember how we could take this, there's a lot of limit properties that hold true for limits that don't hold true for other things. But you can actually take that 2/3 power and you can make it outside and just look at this limit. And if we had this limit, we would say, oh, n divided by n is so strong, it's 1. And so this is the limit as n goes to infinity of 1, which is just 1. So this would be 1 to the 2/3, which is 1. And therefore, inconclusive by the ratio test. Oops. By the ratio test. Sorry about that. Okay. Now we get to the root test. And the root test for convergence or divergence works well for series that involve nth powers. It's important to note that the root test is always inconclusive for any p-series. Okay, so let's remember that, inconclusive for any p-series. Okay, so here's our root test. Let the summation of a sub n be a series? Number one, summation a sub n converges absolutely if the limit as n goes to infinity of the nth root of the absolute value of a sub n is less than 1. Diverges if the nth root of the absolute value of a sub n, that limit as n goes to infinity, is greater than 1 or equal to infinity, and the root test is inconclusive if the limit as n goes to infinity of the nth root of the absolute value of a sub n equals 1. Okay, so sometimes it could be inconclusive. So now let's start looking at some of these summations using the root test to determine whether it converges or diverges. So our first one, notice that these are both going to the nth power. And so if I said, okay, I'm going to use the root test, the limit as n goes to infinity, you know that our a sub n is e to the n over n to the n. If you wanted to, you could say that it was e over n to the n. Okay, that is our a sub n. So when we're using this, it would be the nth root of e to the n, or e over n, sorry, taken to the nth power. Well, look, the nth root and the nth power cancel. So the limit as n goes to infinity of e over n is going to be 0. Since 0 is less than 1, the summation a sub n converges absolutely by the root test. Okay. And I kind of forgot to put the absolute value sign on that, but that's fine. Okay, so this one, we've got going to an nth power, so let's try the root test. Not everything's going to the nth power, but let's just see what happens. So we've got the nth root of the absolute value of n to the third over 3 to the n. And so for this one, I'm going to go ahead and change this nth root to the 1 over n power. So this is the absolute value of n to the third over 3 to the n, and this to the 1 over n power. This is where you're going to see why this works when it's taken to the nth power. Because now we can say, oh, well, I'm going to apply that to both of my terms. And when I apply it to 3 to the n, it gives me 3 to the 1. And so now I can take 1/3 out front because it doesn't have an n in it. And this is just absolute value of n to the 3 over n. And if I put infinity, if I put infinity, I mean, if you're thinking of putting infinity into this n in the denominator of your exponent, you're gonna be thinking of some number to the very close to 0 power. Okay, that's what you need to be thinking of. And anything to the 0 power, you know, if you're talking about a large number, but then you're taking it to the 0 power, that just becomes 1. So this is 1/3. And so since 1/3 is less than 1, the summation a sub n converges absolutely. Okay, here is another one. So we're taking something to the nth power. I think we should use the root test. So the limit as n goes to infinity of the nth root of the absolute value of n over 1 plus n cubed to the n. And since you're taking that to the n, it might be easier just to write it like this. Like that, because these two are going to cancel, because that whole thing's being taken to the nth power. So you can cancel those. So limit as n goes to infinity of n over 1 plus n cubed, absolute value of that. And now you're thinking, oh, well, n over n cubed is so strong, we can just look at the limit as n goes to infinity of n over n cubed, which ends up being 1 over n squared when you simplify, and therefore that goes to 0. 0 is less than 1, so the summation of a sub n, this summation right here, converges absolutely. Okay. So then we go to strategies for choosing a test. We have now explored 10 tests for determining the convergence or divergence of an infinite series. At times, more than one test can be applied. That means that you might get the answer using, the ratio test, the same as if you use the integral test or something like that. You'd get the same answer. So there's not just one answer. There could be, lots of series that you could use this or this or this. But your goal should be to choose the most efficient test. So let's look at some guidelines for choosing an appropriate test with the following examples. So let's look at example A. Okay, it is to the nth power, but notice that this is a constant. This does not have an n in it. It's pi over 3. That is a constant. And so if I have something going to the nth power, but the thing that's going to the nth power is a constant, I'm going to use the geometric series test, right? It's a geometric series. And so therefore, if my r, which my r for this geometric series is pi over 3, and that happens to be greater than, because pi is 3.14, greater than 1, so I know that the series will diverge. Series diverges because it's a geometric with r greater than 1, okay? So we could have maybe used the root test here, but it wasn't the most efficient, okay? Now let's look at the next one. This one is 1 over 4n plus 1. I see that if I was looking at 1 over 4n, that is very similar to 1 over n, which I know diverges. So I'm thinking, well, this one is going to be smaller because it will have a 4 times n in the denominator. So it's going to actually be smaller than the 1 over n. So if you remember back on the limit comparison test, if you have a divergent series that is larger, let's go back to that because I want to say it right. So I'm going back to my 10.3 and my b sub n, because remember it said, I'm just going to do limit comparison test, just to remind us. It said if my a sub n is between 0 and b sub n. Okay, so this would be my a sub n, and this would be my b sub n, right? My harmonic would be the largest. This one is going to be smaller because its denominator is bigger, so that means it's smaller. so this series says if your B sub n diverges. Sorry, I lost my page. Oh, my limit comparison test. I was doing my direct comparison test. My limit comparison test says that if I take the limit as n goes to infinity of my a sub n divided by my b sub n, and I get L such that L is between 0 and infinity, then either both series converge or both series diverge. So I'm going to erase this because that was the direct comparison test, and I wanted the limit comparison test. So limit comparison test has you look at the limit of a sub n divided by b sub n, and if it equals some value L. So for that one, we would be looking, and I'm going to write limit comparison test. I would be looking at the limit as n goes to infinity of this, which is my limit as n goes to infinity and I actually get 1/4. And so since 1/4 is between 0 and infinity, then they either both converge or they both diverge. So for this one, since 1 over n diverges, then our summation diverges. Okay, so again, that was limit comparison test. And it was because it looked so much like 1 over n. All right, let's look at C. On C, I look at this and I think, what happens when n goes to infinity? What happens to my my limit as n goes to infinity of my n plus 1 over 4n plus 1? Well, the n over the 4n are so strong that I can just look at that, and then the n's cancel. So I end up with 1/4. Well, that does not equal 0. So this one diverges by the nth term test. Remember, this means that your values are going to keep adding up to a number. That means that they're not going to 0. And so to get convergence, the things you add on as you keep adding, they have to be basically going to 0 or it's not going to converge. So nth term test on C, which is what you should actually try very first for everything. But I haven't really talked about that much because I've been trying to teach these tests. But definitely think about, if, well, first you think about geometric series, and then you start thinking about, okay, well, wait, does the limit as n goes to infinity equal 0? And then if it does, then you just have to find something to decide, because if it doesn't, it diverges. But if it does, that still doesn't mean it converges. Okay, it means it could converge. All right, let's look at D. On D, we have n over e to the n squared. So when I look at that one, I mean, it does have a power, but I think the most efficient one would be the integral test. And you would be using y equals x times e to the negative x squared. So I would just think of it like that, or x over e to the negative, or x over e to the x squared. But the integral test is the limit as b goes to infinity of the integral from 1 to b of our x e to the negative x squared dx. And your u is negative x squared, your du is negative 2x dx, and so your du divided by negative 2x is your dx. And this becomes the limit as b goes to infinity, integral from 1 to b, x e to the u times du over negative 2x. And really, since my u was negative x squared, negative 1 squared would be negative 1. Because remember, you're putting negative and then putting that in as 1, which gives you negative 1. And then if you put b in, you get negative b squared. So let's just change those to u's. And now you have the limit as b goes to infinity, integral from negative 1 to negative b squared. And I'm going to go ahead and bring that negative 1/2 all the way out front because it doesn't have a b in it. So I don't even have to worry about that either. So you can bring that all the way to the front. So that gives you negative 1/2. And then you have e to the u from negative 1 to negative b squared. So negative 1/2, this would be e to the negative b squared minus e to the negative 1. Now, don't forget our limit. Sorry. And I put that negative 1/2 back in. I didn't mean to because I forgot my limit. But either way, it's fine. So if I distribute that, my limit as b goes to infinity of negative e to the negative b squared over 2 plus e to the negative 1 over 2 and then think of this as negative 1 over 2e to the b squared plus 1 over 2e. And when I put infinity in for b, this goes to 0. And my answer is 1 over 2e. Oops, sorry. My answer is 1 over 2e. And on the integral test, that means it converges. So since that goes to something, then my summation converges. Okay, by the integral test. And hopefully, I mean, you saw all that. I'm going to go ahead and erase this so get it out of our way. I did that whole integral just showing you that, hey, that's how you would do it. You got 1 over 2e. Therefore, summation a sub n converges. Okay, so let's look at E. Alternating. So I'm thinking alternating series test. So first thing is we look at our a sub n, which is 2 over 3n plus 1. And we say, okay, it's always going to be greater than 0. As n gets greater, my denominator gets greater, and so my a sub n plus 1 will always be less than or equal to my a sub n. And then when I look at the limit as n goes to infinity of my 2 over 3n plus 1, I end up getting 0, okay? So therefore, series converges by the alternating series test. F, I'm thinking this is to the nth power, but do you see how all of these have n's in them. So I'm thinking root test. And we would say the limit as n goes to infinity of the, oops, almost put third root, the nth root of the absolute value n plus 1 over 3n plus 1 to the nth power. The nth root and the nth power cancel. And then, of course, this limit, the n and the 3n are so strong that you would, focus on that. The n's would cancel. You'd get 1/3. 1/3 is less than 1. So it converges absolutely. If I get on the edge, it just throws me out. Absolutely, you know what I mean. Absolutely. Okay, the last one has a factorial. I say ratio test. And on the ratio test, we are looking at the limit as n goes to infinity of a sub n plus 1. So this would be n plus 1 factorial divided by 3 to the n plus 1, and then times, because we are flipping that, times the reciprocal of that, because we're really dividing by it, but we say that's the same thing as multiplying by the reciprocal. And then we're going to split it up. This is going to be n plus 1 times n factorial divided by 3 to the n times 3, and then times 3 to the n over n factorial. And so my n factorials will cancel, my 3 to the n's will cancel. This will give me the limit as n goes to infinity, absolute value of n plus 1 over 3. This is going to be infinity. So therefore, summation diverges by the ratio test. Okay, so hopefully that was a nice little kind of, like, oh, let's just take a few and see what we get. So now, this is our summary of tests for sequences and series, okay? So nth term test is probably the one that you should just kind of try and glance at, and all of the ones that could converge, possibly, are going to have a limit as n goes to infinity that equals 0. If the limit as n goes to infinity of a sub n does not equal 0, you can already say it diverges and don't go anywhere else, okay? Geometric. You need to be looking for the geometric, okay? It's going to have a number to the nth power or something like that, or to the, it's gonna end up having a number times a number to the nth power, or something like that. If the absolute value of r is less than 1, it converges. If the absolute value of r is greater than 1, it diverges. You can actually calculate what its sum is by taking the first term over 1 minus r, the common ratio. Telescoping series is the one where it's a sub n minus a sub n plus 1. And what ends up happening is that when you take the limit as n goes to infinity and you get an actual number, then you know that your telescoping series converges. The sum will be the first term minus that number that you get as you take the limit as n goes to infinity, okay? And it's going to be, the telescoping series is in this type of format. P series, it looks like 1 over n to the p. If p is greater than 1, it converges. If p is between 0 and 1, it diverges. If p equals 1, it's also divergent, because that's the harmonic series. Alternating series test, that's if you would have negative 1 to the n or negative 1 to the n plus 1. And if your a sub n plus 1, it has to be, your series has to be positive. That's why they're telling you that these have to be greater than 0. and the nth term has to be greater than the next term. So they need to be decreasing. And all the other things that we talked about, the limit as, well, here it's saying positive and decreasing, and then the limit has to go to 0. If those 3 things are true, 1, 2, 3 things are true, then it converges, okay? And you can find your remainder error bound by truncating it, like taking that partial sum, and let's say you took the partial sum of the first 4 terms, the absolute value of the 5th term. That's what your remainder is going to be, or your error. Integral test. F has to be positive, continuous, and decreasing. And so this is, your series would be this. You would look at the integral. You would change your a sub n to f of n, and then change it to f of x, and look at the integral from 1 to infinity. And it converges when this integral converges. It diverges when this integral diverges. The remainder is going to be between 0 and your integral from n to infinity. Ratio test. This is where you take the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. It converges if it's less than 1. It diverges if it's greater than 1 or infinity. It's inconclusive if it equals 1. Root test. It converges if it's less than 1. It diverges if it's greater than 1 or equal to infinity. It's inconclusive if it equals 1. Direct comparison test. This is the one that I accidentally started talking about instead of the limit comparison test. I should have just gone down here and looked. For the direct comparison test, a sub n has to lie between 0 and b sub n. So b sub n has to be greater. And if this is true, because the one that you're trying to figure out is your a sub n, right? That's the one you're trying to figure out. So if your b sub n converges, then your a sub n converges. Now, if your b sub n is smaller than the one that you're trying to figure out, and your b sub n diverges, then your a sub n diverges, okay? Then lastly, the limit comparison test. So that is the limit as n goes to infinity of a sub n divided by b sub n, where b sub n is some series that you know whether it converges or diverges, like the harmonic 1 over n. That one we know. So you might use that to divide by. But if you divide those and take that limit and you get some answer that is between 0 and infinity, then and you know that your b sub n converges, then your a sub n converges. If you know that your b sub n diverges, then your a sub n diverges. They